Okay, let's try this again. So if we throw together these bases of different eigenspaces, why is it that the resulting sort of concatenation of vectors has to be linearly independent? Okay. Well, instead of proving that in general, which is a little bit complicated, really the only idea in that proof is captured by a simpler example here. Okay, so suppose we have an eigenvector u with eigenvalue lambda, and an eigenvector v with a different eigenvalue mu. And let's show that these two eigenvectors from different eigenspaces have to be linearly independent. Okay. All right. So let's suppose we have some linear relation between them. So suppose that a times u, how about plus b times v is equal to the zero vector. And we need to show that a and b both have to be zero. Right? Okay, well, we need to use the fact that these are eigenvectors somehow, and so we're going to have to apply t to them eventually. So might as well apply t to both sides of our equation as a start. And t of the zero vector, if t is linear, is always a zero vector. And then again, using the linearity of t, we can distribute it over the sum and then pull the constants out, so pull the scalars out. We get a times t of u plus b times t of v equals 0. Now let's use the fact that u is a lambda eigenvector, right? So t of u equals lambda times u. And v is a mu eigenvector. So t of v equals mu times v. So we get that equation. And then on the other hand, let's sort of, starting from the top again, let's bring this all the way down here, but let's multiply both sides by just by the scalar lambda, okay? And so I can move it past the a and get a lambda u plus b lambda u. And then lambda times the zero vector is zero vector. And now you probably see what's going to happen. I'm going to subtract these equations. And the first term goes away. And the next term, that was supposed to be a v, wasn't it? Okay. And the next term, we have a b and a v, which can be factored out. And then in the middle we have what's left over, mu, here, mu minus lambda. That's equal to 0. And, well, remember, we assumed that these eigenvalues were distinct, meaning not equal. And therefore, mu minus lambda is not equal to 0. Okay? And we know that v is non-zero because it's an eigenvector, and eigenvectors are not allowed to be 0. And so the only way this product could be 0 is if b is 0. Okay? And if b is 0, then you just plug it in up here, and you, again, because u is not 0, you get that a is 0 as well. Okay? So that implies that u and v are linearly independent. Okay? So that's how it works for a couple eigenvectors. Here's the general statement. If you concatenate bases of all your eigenspaces for a matrix, pardon me, then that concatenated list, curly b, is linearly independent. Okay, so think again of my example at the top here, where we threw together these bases for 3 eigenspaces. Under what condition on the original matrix would this actually be an eigenbasis? Part A here says that these are always linearly independent eigenvectors, but if they're going to be an eigenbasis, they have to be a basis of Rn, right? Where n is the dimension of your matrix. Okay, and so if this is going to be a basis, then we better be in R6, right? Because there's only 6 vectors there. Okay, so this is an eigenbasis if and only if A is a 6 by 6 matrix. Okay, so you just need to get enough. All right. Basically, if you add up the geometric multiplicities of these three eigenvalues, remember we had geometric multiplicity of 3, of 1, and of 2. Add them up, you get 6. So you have 6 independent eigenvectors, and if you have a 6 by 6 matrix and you're in R6, then you have an eigenbasis. Okay. So in other words, if the sum of the geometric multiplicities, the sum of the dimensions of the eigenspaces, is equal to, I'm sorry, the number of vectors here is this sum of the dimensions of the eigenspaces, and it's an eigenbasis if and only if that equals n, right, where A is an n by n matrix. Okay. And so we know that having an eigenbasis is equivalent to being diagonalizable, so the matrix is diagonalizable also if and only if the sum of its geometric multiplicities equals n. Good. So let's try another example. And this matrix is not going to require a lot of work because it's awfully close to diagonal already. So in particular, we've shown before that the eigenvalues of an upper triangular matrix, which this is, would just be the numbers on the main diagonal, and the only two distinct numbers that we get are 5 and 6. Okay. And moreover, if you think about the characteristic polynomial, it's going to be the determinant of A minus lambda I, so it's 5 minus lambda, 0, 0, 0, and then it's all zeros below the main diagonal, right? And then 6 minus lambda, 0, 1, 5 minus lambda, 0, and 6 minus lambda again. And so it's just 5 minus lambda squared times 6 minus lambda squared. And remember, if we were looking for eigenvalues, we kind of already said what they are, but we would set this equal to 0, and we'd get lambda equals 5 and 6. But I'm doing this because, look, each root here, the corresponding factor has an exponent of 2 on it, right? You get 2 copies of that term. So both algebraic multiplicities are 2. And, but they add up to 4, which is nice, right? Dimension of your matrix. And that'll happen anytime your characteristic polynomial factors completely into linear factors, as it does here. Okay, then these exponents will have to add up to the degree of the polynomial, which is the same as the dimension of the matrix. Okay. But it's not enough for the algebraic multiplicities to add up to 4. We would need the geometric multiplicities to do so as well. And so let's think about what those are. The geometric multiplicity of 5 is the dimension of E sub 5. Whoops. And, well, what is E sub 5? Right, E sub 5 is the kernel of A minus 5i. So take 5 away from the main diagonal, and you get, on the main diagonal, you get 0, 1, 0, 1, and then you still have the 1 up here, and 0 is everywhere else, okay? And so, I guess I could fill those in. All right, and so, well, what's the, see, the rank of this matrix is 2, right? Here's your 2 independent columns, and so the nullity is 2 as well, so the dimension of the kernel is 2. Right, this kernel would be the span of 1, 0, 0, 0. Right, from that first column, and from the third column, we have an element 0, 0, 1, 0 in the kernel. Okay, and that would span the whole kernel. So anyhow, long story short, the geometric multiplicity of 5 is 2. And let's see if we're as lucky with 6. I fear not. All right, so this time we're finding the kernel of a minus 6i. So take 6 away from the main diagonal, and we get negative 1, 0, negative 1, 0. And then we still have a 1 up here. And maybe without me even filling in all the zeros, you can tell that these 1s are all in different rows. Okay, so the first, third, and fourth columns are all independent. This matrix has rank 3 and therefore nullity 1, and so the kernel just has dimension 1, which comes from the fact that the second column here is a 0 vector, so it's going to be 0, 1, 0, 0. That's my basis for E6. Okay, so that geometric multiplicity of 6 is just 1. And if you add up those geometric multiplicities, you just get 3, right? You only get sort of 3 independent eigenvectors here. And that's not enough to make a basis for R4, right? We need 4. And so, well, that's all there is, right? We don't have any other eigenvalues to look for eigenvectors. And so we just have to conclude that there's no eigenbasis for A, okay? And therefore A is not diagonalizable. Okay. And so, yeah, the key thing here is that if you add up the geometric multiplicities, the dimensions of the eigenspaces, the result is less than the dimension of the matrix, right? So you can't get a basis for R4 made up of eigenvectors. Just not enough eigenvectors. Not enough independent eigenvectors, right? All right, well, you've probably been wondering, what's the relationship between the algebraic and geometric multiplicities of an eigenvalue? And, well, up here, the geometric multiplicity was always less than or equal to the algebraic multiplicity. And that turns out to always be the case. Okay, so let me just give you sort of a brief sketch of why that's true, of a proof. Let's focus on a particular eigenvalue, lambda naught. Excuse me. And suppose that it has geometric multiplicity m, so that I have a basis for it containing m vectors. Okay, and there's a theorem that says you can always extend a linearly independent collection of vectors in Rn to a basis for Rn just by adding some more vectors to it. Okay, so take your v1 through vm, add a few more vectors if necessary to get a basis for the whole space. Okay, well now write down the matrix with respect to this new basis for the transformation given by the matrix A. Okay, so you'll get a matrix that's similar to A. And, well, because V1 is an eigenvector for A and for T with eigenvalue lambda naught, T of V1 is lambda naught times V1, right? And so if you try to find the first column of this matrix, it's going to be a lambda naught in the first spot and zeros everywhere else. And similar reasoning holds for the first m columns, right? T of Vi for each of these vectors is going to be lambda naught times Vi. And so the first m columns here look very nice. After that, we have these other vectors we added on. And who knows what happens to those, right? I'm not making any claim about exactly what these columns are here after the mth column. But this is enough information about that matrix to be able to say what we need to. Okay, if we want to calculate the characteristic polynomial of A, well, that's the same as the characteristic polynomial of B. All right, similar matrices have the pardon me, the same characteristic polynomial. And so, if you're going to subtract lambda from the main diagonal here, and then find the determinant of that matrix, well, every pattern that you pick is going to have to contain all of these m spots here, right? Because those are the only non-zero entries in those first m columns. And so you're gonna pick all of those, lambda naught minus lambdas, and then some other stuff from this n minus m by n minus m squared on here. Okay. We don't care about that last part. We just care that the characteristic polynomial is going to have a lambda naught minus lambda to the mth power factor at least. Okay. Now you may get some, just by coincidence, get some extra lambda naught minus lambda factors down here from this part. But you get at least m of them. Okay. That means the algebraic multiplicity of that eigenvalue lambda, it's at least m. It might be bigger. It's at least the geometric multiplicity. Okay. So that's how you prove this fact, that the algebraic multiplicity is at least as big as the geometric multiplicity. Now, that's my closing question for you. I don't have it on the handout here, but that's if, let's see, do I have space to write it down here? Let me try. If the characteristic polynomial of A doesn't factor completely, by which I mean it doesn't factor completely into linear factors. Maybe there's some quadratic factors left, okay? I'm talking about over the real numbers. Then, is it possible for A to be diagonalizable? Maybe pause the video and think about that for a moment. Okay, if the characteristic polynomial of A does not factor completely, could A still be diagonalizable? And the answer is no. And here's why. To see if it's diagonalizable, remember we want to know whether the sum over eigenvalues lambda of the geometric multiplicities of those eigenvalues, whether or not that's equal to the dimension n of your matrix. And, okay, well, each of those is less than or equal to the corresponding algebraic multiplicity. Okay, and so if you sort of add up all those inequalities, you get this inequality of the sums. And if the characteristic polynomial A doesn't factor completely, then the sum of these algebraic multiplicities, the sum of the exponents in the factorization of your characteristic polynomial, I should say the sum of the exponents just on the linear terms, right, is going to be less than n. Because there's at least one quadratic term which is not contributing to the, it's not giving you any eigenvalues, it's not contributing to any algebraic multiplicities. And okay, well, if you string these two together, you see that the sum of the geometric multiplicities is less than n. And therefore, if you, concatenate bases for all your eigenspaces, you're not going to have enough eigenvectors altogether, right? You're not going to have enough to make a basis for Rn. So that's a nice shortcut that, if you can't even factor your characteristic polynomial all the way, then there's no way that A can be diagonalizable. You don't even have to start looking for eigenvectors. You're not going to find enough. Okay, well, thank you for putting up with my obnoxious noises. I apologize. I hope that at least partially made up for having had to miss a lecture on Friday. And if you're having a good weekend, I will see you Monday. We'll start talking about 7-4.